For number 12, we're asked, in an RLC circuit, can the amplitude of the voltage across an inductor be greater than the amplitude of the generator EMF? We're going to look at this in multiple parts. First, the amplitude part. So can the amplitude of the voltage? For the amplitude of the voltage, we've known from previous problems that the formula for this is just I is equal to the alternating EMF over Z. If we paste this down here, we can now look at our next part, which is across an inductor. And maximum voltage across an inductor is just the voltage of our inductor, and that's going to be equal to our I times the XL. Again, if we're asked, can the amplitude of the voltage, which is this right here, across an inductor, which if we look back at a previous problem, we used this formula, I is equal to V of L over X of L. So we can just take this formula right here and paste it in like this. However, we need to convert this because we're looking at the voltage. We're going to say that V of L is equal to I times X of L. And we can just substitute our I with this right here. So this is going to go into here, and we are just going to get that V of L is equal to the EMF times the X of L all over Z. And our question is, can the amplitude of the voltage across an inductor be greater than the amplitude of the generator EMF? Well, if our X of L is greater than our Z, or if this top part is greater than our Z, then yes, it will, the inductor will be greater than our EMF. So this is how we solve part B. It is simply yes for the answer. For part B, we're asked to consider an RLC circuit with a driving EMF amplitude. Alternating EMF is equal to 10 volts. Resistance is equal to 8 ohms. And we have inductance, which is equal to L, which is L, and that's equal to 0.9 henries. And we also have a capacitance, and that is 0.8 microfarads. We're asked to find the amplitude of the voltage across the inductor at resonance. So the amplitude of the voltage, we're just going to be looking for the voltage value across the inductor at resonance. Well, to do that, we can use this formula. We need to find the voltage across the inductor. And this is how we find the voltage across the inductor. V of L stands for voltage across an inductor. So we can take this formula and paste it down here and start filling things in. We know that X of L, we know that XL, we can write this a different way. And we've done this before. For example, up here, where we've written that X of L is equal to L times omega. And if we're not given omega, we can also write this as 2 pi frequency. In the variables that we're given, we can see what we have and what we don't have. What we don't have is an omega, nor do we have a frequency. The only way to solve this is further break this down. So this also equals L times omega, and omega can be also written as the square root, or 1 over the square root of LC. This is another way to write this. Since we can't use the formula here, we can X this out, and we can't use this, we'll X this out, and we are just going to have to use this. If we rewrite our formula, it's going to be V of L is equal to the alternating EMF times L over the square root of LC times Z. And we have all of the rest of our values, so we can just plug these in. Our V of L is going to be set equal to, and we'll do the denominator first. In the denominator, we have the square root of L times C. Our L is inductance, and that's going to be 0.9 henries multiplied by our C. And our C is 0.8 microfarads. We need to convert this, so it's going to be 0.8 times 10 to the negative 6 farads, all under the same square root. And this is going to be multiplied by Z, and Z is equivalent to our resistance. So our Z is equal to R at resonance, and we can just put 8 ohms in place of our Z. Our alternating EMF is given as 10 volts, and we need to put an L up here, which is 0.9 henries. After we carefully plug all of this into our calculator, we're going to get that the voltage across the inductor at resonance is approximately 1,326 volts. And that is the answer for number 12. First we solved for A, showing that yes, the amplitude of the voltage across an inductor can be greater than the amplitude of the generator EMF. Then after this, we found the amplitude of the voltage across the inductor at resonance. We wrote down the values that we were given. We wrote down this formula, and we filled in our x of L using L times omega, which we rewrote as 1 over square root of LC. We plugged these values back in and got this formula. We said at resonance, Z is equal to R, so we were able to substitute in our Z for our R value, which was 8 ohms. And then we plugged everything into our calculator right here and got our answer.